T-minus 10, 9, 8, 7, 6, 5, 4, 3. We have ignition 2, 1, 0. We have liftoff of the United Launch Alliance Atlas V rocket carrying the second space-based infrared systems mission for the United States Air Force.
Information about the weather forecast we see on live television every day, or watching a live football match happening more than halfway across the world. All of this has been made possible thanks to the satellite orbiting the Earth 24/7, providing us with useful images and vital information about the Earth. But the most important use of all, satellite is a major contribution to the communication system as we know today. On the 4th of October, 1957, the Soviet Union has launched the first man-made satellite, Sputnik 1, into orbit. Although it didn't contain any scientific instruments, Sputnik 1 obtained information about the ionosphere. Although the data obtained was not significant, Sputnik 1 marked the beginning of the satellite era. There are several types of satellite that's been orbiting the Earth today. One of them is the astronomical satellites. Astronomical satellites are satellites used for observations of distant planets, galaxies, and the other space objects, helping us to learn about our universe far more effectively than we could achieve on the surface of our Earth. The famous example of this could be the Hubble Space Telescope. Hubble Space Telescope has been in orbit since the early 1990s and still remained in service. It contains a 2.4 meter mirror which helps function four main instruments observed in the near ultraviolet, visible, and a near-infrared spectra. Hubble's orbit outside the distortion of the Earth's atmosphere allows it to take extremely high-resolution images with negligible background light. Hubble has recorded some of the most detailed visible light images ever, allowing a deep view into space and time. Many Hubble observations have led to breakthroughs in astrophysics, such as accurately determining the rate of expansion of the universe. There is also the biosatellite, which is a satellite designed to carry life in space. The very first biosatellite was the Sputnik 2, launched by the Soviet Union carrying a dog named Laika on November 3, 1957. The aim of the biosatellite was for us to study the effect of the weightlessness, radiation, and other conditions humankind will need to know before commencing a spaceflight. Information obtained from the biosatellite inevitably enabled us to have a human space exploration as we know today. One of the most important satellites of all, the communication satellite, which relays and amplifies the telecommunication signals, providing us with the possible usage of live television, radio, and internet, and many other military applications. By transmitting the signal to the satellite through the uplink process, the satellite could then relay the wave back to the receiver station halfway across the world through a downlink process to ensure that communications could be made possible anywhere in the world. The Earth Observation Satellite provides us with detailed pictures about our surface and terrain. Powerful, high-resolution optical device equipped on board satellites like the Sentinel-1 has a span of 290 kilometers and a speed of more than 7 kilometers per second. With this speed, the Sentinel-1 could provide us with a detailed image of the whole Earth in less than 4 days, and it can also be used to track oil spills or the ice melts. The navigational satellite is a major contribution to the Global Positioning System, widely known as a GPS. It uses a series of satellites placed in specific orbits around the Earth to figure out where the receiver is located. The GPS system requires information from at least 3 satellites to be able to obtain the current location with a precision to more than plus or minus 1 meter. With a 4th satellite in place, the GPS system could now determine the altitude of the receiver. Also in the category of satellite is the International Space Station. It is the largest man-made object in the sky, hosting 10 astronauts whose main purpose is to conduct scientific experiments in the field of biology, physics, and astronomy to understand how life could be moved out of the planet. Weather satellite provides us with a weather forecast. It uses an instrument on board called the radiometer to scan the Earth. The measurements are made in form of electrical voltages, which are then digitized and transmitted to the receiving station on the ground. With a weather that is rapidly and continuously changing, the satellite measurements could be made available in less than a minute. Moreover, measurements regarding the solar flares could also be made in a similar manner. But before these satellites can provide us with these useful information, it has to be launched into space. A satellite launch is like any other rocket launches. The first stage of the launch uses kerosene, liquid oxygen mixture, plus a number of solid fuel rocket booster which provides the main source of thrust and brings the satellite up to about 50 miles in altitude. The second stage rocket booster will continue to ascend the satellite up to an altitude of around 100 miles. The third and final stage places the satellite into the desired orbit with the desired speed. When the desired orbit is reached, the satellite will start to extend the solar panels to obtain energy and hence start to operate. But the main question is, how fast must a satellite travel in order to maintain its orbit and not fall down to the Earth? The centripetal force is considered, where m1 and v represents the mass and the speed of the satellite respectively. The centripetal force has to come from the force of gravity, so we combine the equations for the centripetal force and the force of gravity together and rearranging it to obtain an equation for the required speed. This worked example shows a human-made satellite orbiting at around 400 miles above the Earth's surface, or about 640 kilometers. What speed will it require? Well, after substituting everything into the equation, we can obtain that it has to travel around 7,540 meters per second just to stay in orbit. There are several types of orbit, each depending on the altitude. The low Earth orbit covers an altitude of 160 to 2,000 kilometers above the Earth's surface. Most scientific and many weather satellites are in this orbit. The inclination of the orbit will depend on the purpose of each individual satellite. For example, the low inclination orbit with about a 35-degree angle of inclination could be used to monitor tropical areas such as the Tropical Rainfall Measuring Mission, or the TRMM launched in November 1997. The polar orbit circulates between the poles of the Earth and are often used for observation and mapping, such as the previously mentioned Sentinel-1. However, this orbit cannot sense a specific spot on the Earth's surface continuously. Therefore, the Sun-synchronized orbit is used so that each successful orbital pass occurs at the same local time of the day. Medium Earth orbit covers an altitude between 2,000 and 36,000 kilometers away from Earth's surface. The most common use of this area is for the navigation and communication satellites, with the most common altitude around 20,200 kilometers. One orbit in this region that is particularly interesting is the Molniya orbit, invented by the Russians. The unequal elliptical orbit allows the satellite to be over the high latitude area, such as countries located in the far northern hemisphere for a longer period of time. It spends more than 2/3 of the time over one hemisphere. The high Earth orbit defines an area of altitude over 36,000 kilometers. At this exact altitude, the satellite can achieve orbital speed that exactly matches the Earth's rotation speed. This allows the satellite to be placed in the exact same position over the Earth's surface throughout the orbit, making it to appear stationary. This particular orbit is called geostationary orbit. It is extremely valuable for weather monitoring satellites. When inclination is introduced, the angled orbit will be called geosynchronous orbit, but will have the same characteristics as the geostationary orbit. In order to change the orbit, such as changing the altitude, a series of additional rocket burns could be done. This process is called the bi-elliptic transfer, consisting of 3 burns, the first 2 changing the altitude and the last burn to make the final adjustment to the desired final velocity. With the help of bi-elliptic transfer, the rendezvous and docking between two satellites can occur. Critical and sensitive maneuvering technique is applied by making small adjustments to the relative speed of the two satellites until the complete alignment is achieved. During the final approach, the relative speed can be as small as 10 centimeters per second. This speed is used until the docking mechanism is in contact and the confirmation of mechanical capturing system between the two satellites is made. Final checks are then performed to ensure that the same level of pressurization between the two satellites is achieved. If so, the hatch could then be opened and the two satellites are joined. There are 5 locations around the planet's orbit where the gravitational forces and the orbital motion of the spacecraft, Sun, and a planet interact to create a stable location from which to make an observation. These points are known as Zangarian points. Point L1 states the location of orbit closer to the Sun in an orbit which is smaller than the Earth. In this position, Earth's gravity pulls it in the opposite direction and cancels out some of the Sun's pull. With the weak pull from the Sun, the satellite will require less speed to maintain its orbit. If position L1 is maintained, an observation of solar wind can be monitored 1 hour before reaching Earth. Similar to L1, point L2 is located in orbit further away from the Sun in comparison to the Earth, or the night side of the Earth. The extra pull of our planet with addition to the Sun's pull allow the spacecraft to travel faster, keeping pace with the Earth. Several observatory satellites is making use of this region to study the larger universe. Point L3 lies behind the Sun, opposite the Earth. Even though the object at this point cannot be seen from Earth, it offers an opportunity to observe the far side of the Sun. Point L4 and L5 lie 60 degrees ahead of and behind Earth. Objects in this location are resistant to gravitational permutation. Because of this, several objects such as dust and asteroids are accumulated in this region. Interplanetary spaceflight is defined as a travel between planets, usually between a single planetary system. Missions to Mars, Jupiter, Saturn, and even dwarf planets such as Pluto have been explored since 1970. These missions gave us in-depth details about each planet and asteroids, which would be impossible to know if these missions were not conducted. To minimize the amount of fuel needed to travel to these distant planets, techniques such as the gravity-assist slingshot is used where the satellites travel around large mass such as planet or asteroid and use the gravitational force to accelerate itself and use the remaining momentum as the remaining velocity to continue to its path. This technique is widely used on many missions. If the satellite traveled out of our solar system, it enters an interstellar space and is now called an interstellar spaceflight. Until today, only Voyager 1, launched back in 1977, has traveled far enough away from the Earth, reaching the interstellar space in August of 2012. However, more probes such as the Voyager 2 is also projected to leave our solar system. The aim of these missions is to understand at the outer limit of the Sun's sphere of influence and possibly beyond. With all these missions and satellite launches, where do the satellites go? There are more than 500,000 pieces of debris or space junk orbiting Earth, only 6% of which is the operational satellite. Other debris are caused by explosion of old space shuttles and satellites from the remaining fuels, or even the collisions between satellites. The rising population of space debris increases the potential danger to all space vehicles, especially the ones with humans on board. With all these debris orbiting Earth, means of tracking these objects must be accomplished to ensure that the safety of current satellites in the International Space Station. Ground-based electro-optical deep space surveillance track all these debris orbiting Earth with 3 1-meter telescopes to be operated at night. It is capable of tracking objects as small as a basketball from more than 20,000 miles away. Despite all this, continuous effort has been made by different authorities from around the world to try to find a more effective way to explore our universe and continue its effort to observe our planet Earth. In the future, we all hope to efficiently launch satellites in a more efficient way, with more complexity integrated into the satellite, and maybe, one day, we will be able to understand our whole universe and how it all started.